Roland Minton. These are some of my favorite math stories. In this episode, Mathematics is Hardy Golf. We'll look at a simple golf model originally proposed by the great mathematician G.H. Hardy. It is a surprising fact that in 1945, Hardy published an article modeling golf scores. Why do I say it's a surprise? Well, you can get a sense of Hardy's personality in the movie The Man Who Knew Infinity. He had strong ideas about how math should be done, and none of those ideas included anything frivolous. Hardy wrote the book A Mathematician's Apology about these ideas. This was an apology in two senses. It was a defense against attacks on mathematics by those who don't understand math. But it also opened with an apology in the usual modern sense for writing the book. It is a melancholy experience for a professional mathematician to find himself writing about mathematics. Exposition, criticism, appreciation is work for second-rate minds. Ouch! Fortunately, he is not around to pass judgment on what I'm doing here. The book ends with his assessment of the work of the best mathematicians. The real mathematics of the real mathematicians, the mathematics of Fermat and Euler and Gauss and Abel and Riemann, is almost wholly useless. Taken out of context, this is harsher than he meant, but he was not a fan of mathematics done solely to solve a specific real-world problem. He was a big cricket fan, though. Nevertheless, for Hardy to publish a simple model of something as frivolous as golf is quite surprising. Hardy's golf paper explores the problem of whether a steady golfer has an advantage over an erratic golfer of the same ability. A common golfing contest between two players is match play, where each of the 18 holes counts as a separate contest. The golfer who wins the most holes, has the lower score on the hole, wins the match. Hardy starts by identifying three types of shots a golfer might hit. Excellent, he called it the super shot. Average, or bad, which in Hardy language would then be a subshot. Both excellent and bad shots occur with probability p. An excellent shot lowers the golfer's score by 1, while the bad shot raises the score by 1. Since probabilities must add to 100%, the probability of an average shot must be 1 minus p, or 1 minus 2p. For simplicity, we will only consider par 4 holes. That is, a string of 4 average shots will finish the hole in 4. AAAA. AEBA would give the same result. E and B cancel. 2 average shots followed by an excellent shot. AAE would finish the hole in 3 strokes, the excellent shot reducing the score by 1. 1 bad shot would require 5 strokes. AAABA, the bad shot increasing the score by 1, and so on. A smaller p-value indicates a consistent steady golfer. Most shots are average. A larger p-value is a more erratic golfer. Many shots are excellent, and many are bad. Since each golfer has an equal probability of hitting excellent and bad shots, and EB cancel to be the same as AA, it would appear that both should average a score of 4. Hardy found otherwise, and here's why. He compared a golfer with p greater than 0 to a golfer with p equals 0, one who always makes a 4. How can the erratic golfer win? Well, a score of 2 can be achieved with shots EE, probability p times p, or p squared. A score of 3 can be achieved with shots AAE, AEA, EAA, and so on. The first 3 have probability p for the excellent times 1 minus 2p twice for the A shots. The next 2 have probability p cubed. E and B both have probability p. And the last 2 have probability p squared times 1 minus 2p. 2 excellent shots, 1 average shot. The probability of the erratic golfer winning the hole is thus W of p equals p squared plus 3 of the p times 1 minus 2p squareds plus 2 of the p cubes and 2 of the p squareds 1 minus 2p's. That can be simplified to 10p cubed minus 9p squared plus 3p. Hardy then computed the probability of the erratic golfer losing the hole as L of p equals, simplified, negative 35p to the 4th plus 40p cubed minus 18p squared plus 4p. This is harder to compute since there are many ways to make a score higher than 4. He then graphed the two functions w and L to see which was larger. That's a pretty good accomplishment back in 1945 before computers. It turns out that WP is less than L of P for all P values less than about 0.37. Now note that with P equals 0.37, more than a third of the golfer's shots are excellent, more than a third are bad, and less than a third are average. That would be incredibly erratic. So, for reasonable values of P, the erratic golfer is likely to lose. Now, why would this be? Look at the last two entries in the way that the erratic golfer can win, EAE and AEE. The ending E's are wasted, in the sense that EAA or AEA would also win. After the first two shots, the golfer only needs an average shot to finish the hole. In golfing terms, the birdie putt doesn't have to be perfect, just good enough to go in. In an article I wrote for the journal Math Horizons, I computed the average score for a hardy golfer, which turns out to be 4 plus P times the quantity of 1 minus P over 1 minus P to the fourth. That's a bit daunting maybe, but for small, i.e. reasonable, values of P, the P over 1 minus P to the fourth term is very close to 0, and that makes the overall mean very close to 4 plus P. The larger the P, the larger the score, and large scores are bad in golf. As an example, for P equals 0.2, the mean is 4.1992, essentially 4.2. The conclusion is that on a hole-by-hole basis, the consistent golfer has an advantage under the assumption that the p-values accurately describe how each golfer plays. This table shows the breakdown for P equals 0.1 versus P equals 0.2. Notice that in match play, the advantage is not large. And in a one-round tournament with 90 steady golfers and 50 erratic golfers, the odds are in favor of one of the erratics winning, although most would lose badly. Over 4 rounds, the steady golfers have a large advantage. Hardy's golf model has been extended by other researchers. In my book Golf by the Numbers, I looked at a Ryder Cup format where 2 golfers are teammates and their score on a hole is the better of the 2 individual scores. Is it best to pair a steady golfer, avoiding a bad score, with an erratic golfer, the potential for a great score? No. The steady-erratic pairing does have an advantage over steady-steady team, but pairing 2 erratic golfers together is better yet. This ignores psychological aspects and the fact that top golfers all hit more excellent shots than bad shots. Well, how realistic is the Hardy model? Van der Ven and others have done thorough studies of the extended Hardy model where an excellent shot has probability P and a bad shot has probability Q different from P. He has also used scores from professional golf tournaments to test the validity of the model. For a simple model created by a crusty World War II era pure mathematician, it does quite well.